your brain is running right now, on 20 watts. That's it, 20 watts, about what a small nightlight pulls. Now here's the number that should stop you cold. Training a single large AI model can burn over 1,000 megawatt hours of electricity. That's enough to power more than 100 homes for a year. Welcome back to Silicon to Software. I'm Imran, and today we're talking about the AI industry's biggest hidden problem: energy. Here's the situation. AI data centers are eating electricity at a pace nobody planned for. The International Energy Agency says AI-focused data center power use jumped 50% just in the last year. And by 2030, total data center electricity demand could roughly double. That's more power than Japan uses, total. In Ireland, data centers already eat up 1 in every 5 units of electricity on the grid. And that number's climbing fast. So why is this happening? Honestly, it comes down to architecture. And every chip in your laptop, every GPU in a data center uses something called the von Neumann design. Memory sits in one place. Processing happens somewhere else, which means every single calculation involves shuffling data back and forth between the two. That shuffling burns energy, it generates heat. Engineers call it the memory wall. Your brain doesn't have this problem. Memory and processing happen in the same place, in the same neurons. And here's what's fascinating. Most of your neurons aren't even firing at any given moment. They activate only when there's actually something worth processing. That's the blueprint chip designers are now copying. It's called neuromorphic computing. Brain-inspired chips built to think more like neurons and less like calculators. Intel's already built one. It's called Point. 1.15 billion artificial neurons deployed at Sandia National Labs. IBM's got their own version too, called NorthPole. And a company called BrainChip is shipping neuromorphic chips for edge devices right now, cars, sensors, IoT hardware. The efficiency gains here are real. We're talking orders of magnitude lower power draw on the right workloads. But let's be honest, this isn't a silver bullet. Not yet. Here's the catch. Today's AI models are trained using a method that doesn't translate cleanly to neuromorphic hardware. The math just doesn't line up. Researchers are working on it, but running something like GPT on a neuromorphic chip today, that's just not happening. Most realistic estimates put broad commercial deployment 3 to 5 years out. That's an industry guess, not a guarantee. Now here's why this matters. Even if you're not the one designing the chip, every AI query you send is pulling real electricity off a real grid, and that grid is already strained. Equipment shortages, connection delays, longer waits for transformers and turbines. Energy isn't a footnote anymore. It's becoming the hard ceiling on how fast AI can grow. Neuromorphic chips won't fix that alone. But they're one of the more credible paths toward AI that doesn't need its own power plant just to run. Worth watching, especially next time your phone battery drains fast after a long AI conversation. That's it for today. For the full written breakdown, sources, and diagrams, head to silicontosoftware.com. I'll see you next time.